Now we're at the A1900 Fragment Separator. It is effectively 35 meters of magnets in a row. There's one, there's one, there's one. There's two different kinds of these magnets. The big gray ones, which actually look kind of like a pie wedge from the top, these big gray ones separate different kinds of nuclei as they come through. Kind of like a prism separating colors of light. So I like to think of it's magnetically separating isotopes like prisms can separate light. And so you can actually select, depending on what you tune the strength of this magnet to, you can select for the kind of nucleus you want, and that will make a 45-degree turn. There's actually 4 45-degree turns here. So this is a slalom, essentially. We tune the strength of these magnets so that only the nuclei we want will make these turns and come out the other end. So this is how it filters. In essence, this system, all 35 meters long of it, is sensitive enough to pick one nucleus out of a million billion others. And so it's good at getting rid of the junk, essentially. It's really, really good at that. So you can do a useful experiment, basically. Now this kind of acts like a prism. This magnet acts as a lens. These are magnets, quadrupole magnets, that effectively focus the beam and keep the nuclei traveling in the right direction, where we want them to go next. So they need it, otherwise they will fly off on you. And we have a whole bunch of these. There's actually 3 magnets inside here. Again, coils of that same superconducting wire I showed you. You're of course going to see the steel yokes, that's what we call them. These are the shells that essentially focus and contain the magnetic field. But of course there's a lot of layers inside, the cooling, the wire itself, you'll never actually see. Just in case you forget where you are and who is paying the bills, there you go. That's useful, that's important. But in here you'll see the same systems that I mentioned before. Power, right there. Cooling, these pipes here, carrying liquid nitrogen and liquid helium. The thin wires, telling this stuff what to do, getting information back. Vacuum pumps are sitting right there on that little platform. Under vacuum all the time. So there's a lot of things that have to happen. Again, 500 people. You have to make sure all these things work in concert. They told me, I love this, if everything, all the systems here only worked at 99% reliability, so only broken 1% of the time, then we never actually do an experiment. We need to be better than 99% reliable on everything to do an experiment. So they're really good at what they do, those 500 people. We steal the best people from all over the world. That's how we do our job. So they're good, needless to say. Any questions about the fragment separator?
Is this part really necessary?
You know, in general, you disconnect something, I bet you it wouldn't work anymore. Everybody's always asking, well, what if I unplug this? I mean, you know, you see these masses of wires, right? Somebody has to know every part and how to fix it efficiently. Yeah. Every hour of research here is effectively worth $5,000. If something breaks, fix it fast. That's the key. So again, they're really good. Really, really good at what they do. Especially diagnostics. Ooh. The whole lab, oh my gosh. Cost of the, now here's the thing. The cost of the lab, because we built it up over the last 50 years, it's really hard to say. You know, our operating budget is over $20 million per year. So you know, you can work that out. And then of course the capital expenditures are tremendous. Really. I mean, it's hard to say. For this new laboratory that we're going to, you know, the new accelerator we're going to add, I mean, it's a $600 million project. I wouldn't be surprised if what we have now is worth that much. And of course, that's over a very long time.
I didn't hear what he asked, but...
Oh, he asked the total cost of this laboratory as is.
Oh, okay.
It's a lot.
What do you do if the new one is built with all the stuff you rip out? Is it somebody gonna...
Excellent question.
Third world...
we will not need the cyclotrons anymore when we add this new accelerator. Nobody really knows at this point where they're going to go. They could be donated to another lab. There's precedent for that, actually. Some of our equipment has been donated from other labs. And, you know, who else needs a cyclotron? Well, other nuclear science labs could use them. They still work. They're fine. Also, they could be actually sold to a medical isotope facility, because they can be used to make medical isotopes and sold to hospitals. There's actually a third cyclotron on campus in radiology that does exactly that. So that could be. They won't show up on eBay, I guarantee you. But that's, aside from that, we don't really know. We'll see. But yeah, it's the price of progress. Constantly. And I will show you as we walk around the things we're changing. It's ridiculous. It's ridiculous. Any other questions? Very good. Okay, you've seen where we make the nuclei we want to study. Now I'm going to show you a bunch of detectors that we actually use to measure